Okay, so here we go. Here's our problem of the day. It's another rocket problem. Now, you might remember we did one before which involved rockets, and that time when we had a rocket, it was in a two-dimensional setting. So this time, we're going to have a rocket. It's going to be a three-dimensional setting. So we have a two-stage rocket again. It's going to move through three-dimensional space. Initially, where it's launching from, it's at the point -3, -4, 1. And as we said, there's these two stages. And in the first stage, for every unit of fuel, you're going to move 2, 3, 5. So essentially, that's how much you move, or the change per unit of fuel. In the second stage, you're going to be moving 1, 1, 2. Now, what's the goal of the rocket? Well, it has to deliver something. In this case, the rocket wants to get as close as possible to a small moon located at position 4, 4, 11 halves. And the problem is, okay, how much fuel should it use in each stage? Now, your first inclination is, well, let's just move the rocket to 4, 4, 11 halves, and that's as close as possible. But the question is, can it get there? So let's think about what's true. You might see words such as close as possible and say, ooh, we're doing calculus today. But no, we're going to still rely on geometry. And we're going to think about the intuition. So let's sort of build up our understanding here. So first off, let's ask the question. So instead of trying to find a specific point, the first question is, what can the rocket reach? So in other words, can we figure out all the points where the rocket reaches? And if we can, once we have those set of points, we say, I'm going to pick out just the right one from among that collection. So let's start off very simply. Suppose I have a single point, and I just talk about the first stage. So what are the type of points? In other words, suppose it's a one-stage rocket. I launch, I blast off, and I look at all the points I could reach based on my fuel. What shape would I be seeing? You'd be seeing a line. Now you might say, well, it's a one-sided line. If it's just one stage, well, we'll pretend like we can launch in the exact opposite direction. So if it's just a one-stage rocket, then that first stage, I can get to any point on that line. Now comes the stage 2. All right, we've spent our fuel on stage 1. We say, okay, now launching stage 2. Well, what's going to happen? From a certain point on the line, which is where I've reached, I'm then going to launch off on stage 2. So that's going to be a line. But of course, you remember, I can launch from any line I want. And so what's going to happen is if I look at the collection of all possible points, it's a combination of a line segment moving so much in this direction and a line segment moving so much in that direction. The moral of the story, and sorry it's a little bit faded there, but we'll draw it in. The answer to what can the rocket reach, the answer is a plane. All right, that's also very faded. Okay, we're going with dark colors from now on. So a plane. So I can get to any point on a particular plane. So essentially, the moral here is if you have freedom to move in one direction, you're going to get a line. If you have freedom to move in two different directions, you're going to get a plane. And you could say, well, what if I have freedom to move in 3 different directions? What would you get? You get space. You'd be able to get it anywhere. And so, you know, if you're a bureaucrat or saying, look, we need more money, just say, hey, let's not make 2-stage rockets anymore. Let's make 3-stage rockets. But, you know, all right. So we have to work with the technology we have, 2-stage rocket. So now we have a sort of a partial answer to what can the rocket reach. We know it's a plane. But that's not really an answer. It's just sort of the category. What we want is like, which plane is it? So we have to start thinking, how can we form a plane? Well, what information do we need to make a plane? We need a normal vector and we need a point. Do we have any one of those for free? The point's for free because we know where we're launching from. So we know that this plane has to have the following point. The point -3, -4, +1. Now, do we have the normal vector? In fact, we have two vectors here. Which one of those is the normal vector? Neither of them is the normal vector. That's the correct answer, because that would make the problem too easy. No, that's not why. Why does neither of these vectors represent the normal vector? What's wrong with these two vectors? They're all on the plane. Yes, or you could say they're parallel to the plane. We need something that's perpendicular to the plane. So the thing is, currently, we have one vector which points in the direction of the first stage, and we have a second vector which will point in the direction of the second stage. But both of them are in the plane. We want something perpendicular to the plane. So what can we do? We use cross product. Yeah, because if you have two things which are perpendicular to what you want, the cross product will give you what you need. So in particular, if you're looking for a direction, you say, well, I know that my direction has to be perpendicular to, this is a shorthand notation for perpendicular, has to be perpendicular to what happens in stage 1, 2, 3, 5, and it has to be perpendicular to what happens in stage 2, 1, 1, 2. And now, I know it's perpendicular to two things, I take the cross product, that gives me the right direction. So the cross product, I'm going to take 2, 3, 5, cross 1, 1, 2. And so I, J, K, 2, 3, 5, 1, 1, 2. So I times 3 times 2, that would be 6I. J times 5 times 1, that's 5J. K times 2 times 1, that's 2K. 1 times 3 times K, 3K, but we subtract. 1 times 5 times I, that would be 5I, but subtract. And 2 times 2 times J, that would be 4J, but again, subtracted. So putting this together, 6I minus 5I gives us 1I, which means 1 in the first entry. 5J minus 4J is 1J, 1 in the second entry. And 2K minus 3K is minus K, which is minus 1 in the last entry. So 1, 1, -1. All right, and we can check. Take a quick dot product. 2 times 1 is 2, 1 times 3 is 3, and -1 times 5 is -5. Add those up, you get 0. Similarly here, 1 times 1 plus 1 times 1 plus 2 times -1. Add those up, you get 0. That means this is the right direction. All right. Great news. We now have our normal vector to the plane. We have our point, and so we can write down our equation for the plane. So it's x, y, z. So these are the coefficients. So a, b, c. So if I think of this as a, b, c, then we get ax plus by plus cz equals something. So the question is, well, what's the something? What goes there? Right, that's where we plug the point in. So it's -3, -4, -1, which would give us a grand total of -8. All right, so we can now answer the question. We can reach any point on the plane that has the form x plus y minus z equals -8. Now, here's the question. Maybe we got lucky and 4, 4, 11/2 is on the plane. Then we can get right to our moon. Well, 4 plus 4 minus 11/2, does that equal -8? No. It equals something, but it definitely doesn't equal -8. All right. So now we have this thing we have to figure out. So we now know all the points we can reach. So what's going on? Well, we have this plane somewhere in space, and then we have this point off the plane. And our goal is we want to get to the point on that plane. That's our goal of where to get the rocket to. We want to park it on the closest point from the plane to that point in space. So we start thinking of the geometry, because geometry is really good. And you might say, hey, last time we did a formula for distance. And we can say, we could use the formula. But we want to be a little bit careful here because we're not just interested in the distance. What do we need? Well, the way to figure it out is drop straight down. And when I say drop straight down, so this would be perpendicular, this point right here, that's where we have to park the rocket. That's our goal as to where to get the rocket to. All right. Well, okay, now what do we need? Well, again, knowing the distance is not enough because what I need is I actually need the coordinates of this point. I need the x, y, z coordinates of that point. So I want to go even further than just saying how far is the moon to the plane. I want to say where is that closest point. So how can we figure this out? Any thoughts?
Well, if you find the distance and then make the normal vector negative, couldn't you just scalar it and then it would be that point?
Well, we could find the distance. We could make the unit vector normal. That can work. That is one way. Is there another idea? I'm not saying that it won't work. I'm just saying that it can work. There's a small catch, which is you got a 50-50 chance of being right. Then you have to check two things because the direction can go in two different ways. So here's sort of my thought. You don't have to use it, but it can work. Just think about this and extend it. What do you see if the color were a little bit darker? You see a line. And so you say, okay, here's what we can do. Let's find this line. Because I claim we actually have the information we need to make this line. Let's review. What do you need to make a line? Point in a direction. Do we have a point? Yeah, what's the point going to be? 4, 4/11 halves. The moon. We have our point. Now, do we have our direction? The normal vector. Because this line should be perpendicular to the plane, which means the direction of the line has to be a direction that's perpendicular to the plane. By definition, that's the normal vector. The normal vector is the direction which is perpendicular to the plane. So the direction is going to be the vector 1, 1, negative 1. And therefore, I can make this line very quickly. I can say x is 4 plus t, y equals 4 plus t, and z equals 11 halves minus t. The 4, 4, 11 halves coming from the point, and then the coefficients for t, that 1, 1, negative 1, coming from the direction. All right, so I can find that line. But I don't need the line. What I need is the point of intersection. So I need something which satisfies both. It's on the line and it's in the plane. So I have to combine these two things together. So what's the way to do that? Well, the answer is plug x, y, z into this equation. Because what you're really after is you just need to know at what value for t do you hit. All right, so we plug that in. And if we do that, so I'll just write this equation again. So x plus y minus c equals negative 8. So we're plugging these in. So we're going to get 4 plus t plus 4 plus t minus 11 halves minus t equals negative 8. All right. And if we do that, what do we get? Well, we get 8. Well, okay, hold on. Let's see. 8 minus 11 halves. I'm just going to write 8 minus 11 halves for right now. How many t's do we have? We have 3. Be careful with this minus sign, because a lot of people will miss this minus sign. Remember, it goes in to both terms. So there's 8 minus 11 halves plus 3t equals negative 8. So we can say 3t is negative 8, then minus 8, and plus 11 halves. All right, well, that's negative 16, that's negative 32 halves plus 11 halves, which is negative 21 halves. And that's 3t. So what do we know about t? Negative 7 over 2. Now, is that our point? No, because it's not a point. It's a value for t. So, but what do we do with that? We plug it into the line. So, what do we get? Well, we get that x should be 4 minus 7 halves, y should be 4 minus 7 halves, and z should be 11 halves minus 7 halves, which translates into what? Well, 4 is 8 halves. 8 halves minus 7 halves gives us 1 half. Again, another 1 half. And here I'll have 11 halves minus 7 halves. That's 18 halves, which is 9. Which tells us that this point, the point that the rocket can get to, which would be the ideal point, the nearest point, is at the coordinates 1 half, 1 half, 9. All right, so we've made progress. Now, are we done? No. What we've done so far is we've now figured out where we need to get the rocket to. So the last thing to do is say, okay, let's review where we're at. We said, look, where can the rocket get to? Well, the rocket can get to anything on this plane. All right. Then we said, all right, let's figure out which part of the plane we should actually get to. And now we figured that out. To finish it up, what do we need to do? Well, we need to figure out how do we get there. So, where do we start? We start at negative 3, negative 4, 1, and we want to end at 1 half, 1 half, 9. So what's the vector? Well, if I start at negative 3 and I end at 1 half, what was my change? The answer would be 7 halves, 3 plus a half. All right, so I need to change my first coordinate by 7 halves. If I start at negative 4 and I end at 1 half, how much do I need to change? 9 halves. And if I start at 1 and I end at 9, how much do I need to change? I need to change by 8. So that's the amount I need to move the rocket. Finally, we get back to the problem that we did a few days ago and say, look, I just need some combination. So A times this vector 2, 3, 5 plus B times this vector 1, 1, 2. That needs to equal the 7 halves, 9 halves, 8. A and B, that is our answer. A is how much we want in stage 1. B is how much we want in stage 2. So once we find A and B, we're going to be done with this wonderful problem. All right. So what do we get? Well, 2A plus B. So that's the first coefficient. That's got to equal 7 halves. And then the second one, we can get 3A plus B, and that's got to equal 9 halves. Well now, can't quite see that. There you go. This is enough to figure out what A is. What can you do? Well, subtract the first equation from the second equation. If you subtract the first equation from the second equation, what do you see? The B's cancel. 3A minus 2A gives just A. So that would be 9 halves minus 7 halves, also known as 1. So A has to be 1. Now that you know A, plug it into either one. Let's say plug it into the first one. You get 2 plus whatever B is has to equal 7 halves. So B should be 7 halves subtract 2. 7 halves subtract 2? 3 halves. And there's our answer. So 1 unit of fuel in stage 1, and 3/2, or you could, if you want to sound very technical, sound like an engineer, 1.5 units of fuel in stage 2. That's the amount of fuel we should do to get our rocket as close as we can to that moon. All right, that was pretty good. I like this one. To be honest with you, I was thinking about putting this on the test. And I said, this is too easy. Got to put something more challenging on the test. No. That's not what I thought. I thought it's a good problem. It's sort of like you got to sort of work your way up. There's nothing particularly hard in terms of the computation, but there's some thought you have to put into it. So it's not an easy problem in terms of the geometric intuition. Okay, are there any questions about what happened on this one? Okay, good. That's great. Wonderful. Now, if you like these types of problems, there's a lot of them on the quiz next week, and there's even a lot more that you can practice with. So, lots and lots of good problems. So let's get to today's topic. And today is a nice, light, relaxing day. So we're going to start by reviewing conic sections really quickly. Now, the word conic sections comes from the idea that you can start with a cone. So if you start with a cone, and when I talk about a cone, I mean a cone that looks something like this. And the question became, and this is what the ancient Greeks thought about, so they said, well, how can I slice the cone? And the answer is, depending upon how you slice it, you can get different things coming out. So for instance, you could take a slice that looks something roughly like that, and when that intersects the cone, what do you see? Well, if it's nice and parallel in some sense, or perpendicular to the cone, you'll see a circle. If you tilt it, you'll get an ellipse. So ellipses come from slices of cones. Now, there's other things you can do. Another way you could have sliced your cone is you could do something like this, where you slice roughly like that, and then you see you get a little bit of the top side, and then you get a little bit of the bottom side. All right, so you could have sliced in that way, and if you do that slice, what do you get? You get a hyperbola. And the last thing is you could say, well, how do you get that last one? Because there's one more that says parabola. And again, you're going to slice, but now what you do is you slice parallel in some sense. So if you think about this as sort of a line, say, look, if I slice nice and parallel to that, what will happen is I'm going to only get one side. And that shape that you get out is a parabola. So by looking at these various slices, you can get these different curves out. So they were called the conic sections. Now for us, when we look at these, we say, well, we can express these in a nice way. And by doing things such as shifting your coordinate system or tilting your coordinate system, your conic sections basically have the form either x squared over a squared plus y squared over b squared equals 1. And that's the ellipse. And if you're wondering what are A and B are what we call the lengths of the axes. So how far are you in the x direction? How far do you go in the y direction? You have the parabola, looks like some multiple of x squared, y equals cx squared. And the c will either squish it or stretch it depending upon what c does. And then you have hyperbolas, x squared over a squared minus y squared over b squared equals 1, or y squared over b squared minus x squared over a squared equals 1. And again, the a and b are essentially moving things in the x and the y direction. Now what we want to do is do the three-dimensional equivalent, and we're going to call these quadric surfaces. And so how do we get a handle on these? And what we do is we say, okay, so the way we're going to understand a three-dimensional object is we're going to look at these cross sections, these slices. So you can see that there's sort of a ghost of a three-dimensional object here. It's a little bit light here. I'll try to sketch in a little bit more. So there's this three-dimensional object here. That looks something like that. And what you can do is you can look at the different slices, and depending upon what level you're at, you'll see something a little bit different. Now, what we do when we're actually looking at these slices is we stack them all on top of each other, and that's going to get into something called level surfaces, contour lines, and that'll be after our first exam. So, okay. So we want to sort of explore these surfaces that are built up. And when we're looking at surfaces, we're going to look at things which essentially have square terms in them. We know what flat things look like. ax plus by plus cz equals d. We want to say, well, what if you start introducing some squares into your pictures? What do things look like? And to help us understand, if we can get a grasp of what the cross sections look like, we can get a good idea of what the surfaces look like. So we have a whole menagerie of surfaces to look at. All right. Well, let's start with this one. Z squared equals x squared over a squared plus y squared over b squared. Now, if you want, just think of a and b as being 1. So z squared equals x squared plus y squared. And we want to think about, well, okay, what do we see? What do we see? Now, when we talk about the question, what do we see, we're really asking, okay, let's think about our slices. So when we think about a slice, how can we slice? Well, you can slice with planes which are of the form z equals a constant. That's usually the most common kind that we'll see, especially as we go on in the course. Or we can fix x equals a constant or y equals a constant. Those tend to be the slices we look at. So let's think about what's happening as we say take different slices. So suppose I look at the xy plane. So in the xy plane, I get z equals 0. And so if this is 0, when is it true that x squared plus y squared equals 0? Well, x squared plus y squared equals 0 could only be true if both x and y were 0. Because if either one of them is 0, it's going to bump you up and it's going to move you away. Now, suppose we move up. Suppose I say z equals 1. So now I've moved up here, so I'm in this slice, z equals 1. 1 equals x squared plus y squared. What do you see? You see a circle of radius 1. So if you move up to height 1, you're going to see a circle of radius 1. What would happen if you moved up to height 2? 2 squared equals x squared plus y squared. What do you see? Circle of radius what? So 2 squared equals x squared plus y squared would be a circle of radius 2. So move up to height 2, get a circle of radius 2. What if you moved up to height 3? What would you see? A circle of radius 3. And so what you're seeing is you're seeing circles that as you move up, sort of the circles are opening up at the same rate that you're moving up. Now that's in the positive z direction. If you move down, what do you get? Well, if z equals negative 1, well, the square, it does the same thing as a positive 1. So it's going to look the same on the other side. The circle radius 1 at distance 1. So, well, what are we seeing? Well, when we take slices with respect to z, so perpendicular to the z-axis, what shape do we see? We see circles. Or more generally, if we let a and b vary, we see ellipses. All right. Is this enough for us to figure it out? Can you see what shape does this? This is a cone. So it's a cone. Now, we could have sliced in a different way. Suppose I fix a slice, and let's say for a moment I go perpendicular to the y-axis. Y-axis, x-axis will still see the same behavior. If we take a slice there, what are we going to see? Well, suppose for a second I fix y equal 1. So when I say I'm perpendicular to the y-axis, it means I fixed a y value. So if I see something like the form like z squared equals x squared plus 1, what kind of shape am I forming in my cross section? This could also be written as z squared minus x squared equals 1. What do I see? Yeah. So whenever I see a difference of squares, that's a hyperbola. And if you think about what's happening when we take this cross section, we see a hyperbola in this cone. All right. So z squared equals x squared plus y squared, that's a cone. All right. How about this one? X squared over a squared plus y squared over b squared equals 1. What's our shape? Well, let's think of our slices. So suppose I look perpendicular to z. What do I see? So say that I set z equals 0. What's the shape? It's like an ellipse. Now suppose I'm perpendicular to the y. In fact, let's set y equals 0. What do we see? See an ellipse. So if I set y equals 0, there's an ellipse. Now, let's do one more. And let's set x equals 0. What do we see? See an ellipse. So what we're seeing is that if we take just these nice cross sections, we're seeing this shape. And now we sort of say, oh, in fact, in general, if I choose a value for x, y, and z, what I'm going to see is I'm going to see either some form of ellipse, or maybe if I go far enough out, suppose I chose x equal, suppose it was a, b, and c were all 1. And I said, well, suppose x was 100. So I had 100 squared plus y squared plus z squared equals 1. So in other words, I was taking a slice way out here. Well, I'm not going to hit anything. Sometimes your slices are empty. That's okay. So the question is, what's this shape? Do we have a nice name for it? Yeah, so this would be a sphere, and that would be the case when A and B and C are all the same. Do we have a name if they're not all the same? An ellipsoid. So you can just think of it, it's like an ellipse, but then it's like oid, ellipsoid. So, all right. So those are going to be some nice surfaces that we'll see later on. Okay, well, let's try another one. X squared over a squared plus y squared over b squared minus z squared over c squared equals 1. So one way to think of this is we can think of it as, again, don't worry so much about the a, b, and c. A, b, and c are more or less just dilation factors in the x, y, and z direction. So if you're just trying to build up your intuition, just suppose they're equal to 1. So suppose, for a moment, we set a, b, c equal to 1, and let's move this z squared to the other side. X squared plus y squared equals 1 plus z squared. So what's going to happen as we vary z? So if you're taking slices with respect to the z-axis, in other words, perpendicular to the z-axis, what do we see? Well, you put in values on this side, you get x squared plus y squared equals something. So what's our shapes going to be as we take perpendicular to the z-axis? They're going to look like circles. Now let's think about the picture. So when is the circle going to be as small as possible? What's the smallest radius? Or what's the right value for z? At z equals 0, the radius is small. So in fact, it's the radius of circle 1. Okay, so that's at z equals 0. Now, as we move up, our radius is going to expand. So it's going to get bigger and bigger. So up here, it's going to be a bigger radius. And then down here, it's going to be a bigger radius. So we have at z equals 0, you have the small radius, and then it's opening up as you move up, and it's opening up as you move down. All right. Now, it's not the x squared plus y squared equals z squared. The 1 in some sense, there's a little bit of a shift. But not too dramatic, not too dramatic. Okay, so what do we see in our slices? Well, if we're perpendicular to z, we're going to see ellipses, or circles. So let's suppose now we fix one of our other variables. Suppose we're perpendicular to x. So if I choose x to be a number, let's suppose for a second I choose x to be 0. What do I see? Say what? It's a hyperboloid. Yeah. So what I see is I see a hyperboloid. So if I'm perpendicular to x, or if I'm perpendicular to y, what do we see? Hyperboloid. We see hyperboloids here. Excuse me, Freudian slip. Hyperbolas. We see hyperbolas. All right. So what we see is in these directions here, we see these types of hyperbola shapes coming out. Okay. So what is this looking? Well, sometimes this is called like an hourglass type shape, but that doesn't sound very technical. What's a better name for it? Hyperboloid. It's essentially it's a nice sort of three-dimensional generalization of hyperbolas. So that's the shape we're forming. So hyperboloid. So the cross sections are circles, ellipses, or they're hyperbolas, depending on which directions we go in. All right. Suppose we change it a little bit. Minus x squared over a squared minus y squared over b squared plus z squared over c squared equals 1. Now essentially what have we done is we flipped the signs on this left-hand side. So instead of plus, plus, minus, it's now minus, minus, plus. Well, the moral of the story, it's very similar. Very similar. Again, a, b, and c are, you can think of these as dilations. So for now, building up your intuition, set them equal to 1. And we can rearrange this. And if we rearrange this, we can actually rearrange it in the following way. X squared plus y squared would be equal to z squared minus 1. That's what it would rearrange to. Now at this stage, we say, okay, well, let's start taking our cross sections. Suppose I take the cross section at z equals 0. What do I see? I don't see anything. Because if z equals 0, I'm trying to find points where x squared plus y squared is equal to negative 1. There are no such points. All right. So what do we do? Well, let's think about what happens. So when I look at just the xy plane, there's nothing there. I start moving up. So I increase the value for z. When does something interesting happen? At z equals 1, there's something interesting. What happens at z equals 1? I get x squared plus y squared equals 0. Which means I'm going to see just a single point as I move up. So as I start moving up, I don't see anything until I hit z equal 1. And then I see, it's a single point. And then what do I see? So what's going to happen after that? Suppose z equals 2. What do you see? Well, 4 minus 1 is 3. So you get x squared plus y squared equals a number. So what do you see as we go further up? You see circles. There's going to be a circle. And what happens upstairs, symmetry, you're going to see the same thing happening downstairs. So if we're perpendicular to z, we either see nothing, which, I don't know, have you ever seen this symbol before? For nothing? I don't know if they teach this. Has anybody seen this before? Anyone? Anyone? 1 or 2 people have? Okay. It looks kind of like 0, doesn't it? It's not 0. Some people like to think it's phi. It's not phi. Does anybody recognize it?
They use it for me for like no solution.
Right? Right? It's used for no solution. It usually stands for empty set, but you recognize where the actual symbol comes from.
It's like the no smoking sign or like we don't do this sign.
It does look kind of like that. It has that feeling, but it predates that. this was back in the days when smoking was still cool. Don't smoke. No, I'm not saying it was never really cool to smoke, but okay. So the answer is this is actually a letter in the Norwegian alphabet, and it means So that's what it is. It's So like if someone asks you if there's a solution, you go and you're like, that's right. There are no solutions, right? See. So, anyways, all right. Side note, not important. Okay, so either you see nothing or you're seeing these ellipses/circles. It just depends. So you have sort of this sort of like no man's land in the middle here. But then you see circles up high and you see circles down low. Now, suppose we go perpendicular to one of these other axes, either x or y. What do we see? So suppose I say x equals 0. Minus y squared plus z squared equal 1. What is that? It's a hyperbola. So these are going to be hyperbolas again. And so what's going to happen is if we take a cross section here, it's not going to be a cone because it's not cones look like V's. And so they're not cones, but they're more rounded. And so what's our shape? Well, our shape sort of looks like an upside down, two cups, one upside down, one right side up. Of course, they keep going. So this is the shape that we're forming. You can imagine we get this nice shape. Now the question is, well, what do we call this? Well, because we have the same types of cross sections, it makes sense to give it the same type of name. But these two objects are somehow not really the same. They have very different behavior. Now, what do I mean by that? Well, on the right-hand side, we see there's really two different parts. On the left-hand side, there's just one single part. And so we wanted to come up with a little bit more of a distinction. So we're going to refine it. So this is a hyperboloid of one sheet, which is just a fun way of saying it only has one part. And then this is hyperboloid of two sheets, which says, this one splits into two parts. But we see our hyperboloids. All right, now I will say, up to this point, these are mostly just sort of some fun examples. They're not going to be super critical. What we're going to talk about in the next two are important. So we do have to make sure that we understand the next two. All right. The good news is, it should not be so bad. All right. So, z equals x squared over a squared plus y squared over b squared. What do we see here? Well, let's think about cross sections. As we let z vary, well, if it helps, just think of a and b being 1 for now. Z equals x squared plus y squared. Well, if I pick a value for z, if I pick a negative value, I'm not going to see anything because x squared plus y squared can't be negative. X squared plus y squared equals 0. That's just the point 0, 0. And if x squared plus y squared equals a positive number, what's happening? We see circles. So we see that the cross sections perpendicular to z are going to be our nice circles or our ellipses. Okay. So we start here, and then we're going to see some circles moving up. What if I go perpendicular to, say, x or y? What do we see? So suppose we just cover up y equals 0. What's that forming? Z equals x squared. Looks like a parabola. I cover up the x. It's a parabola. And so what's happening here is I'm seeing parabolas. So I'm seeing those shapes. So parabolas. And what do we see? We say, so what this looks like is a nice shape. It's not quite the same as a hyperboloid. It's a little bit more better shape. There's not a second part underneath. So this is any guesses? Paraboloid. But normally we're friends here. And friends we can be more informal. So we can say this is like a bowl. So when we talk about a bowl, we mean usually like a paraboloid. And this is a bowl that opens up. We could make a bowl that opens down. If we wanted to turn it upside down, what would we do? We just put negative signs here. Negative x squared over a squared, negative y squared over b squared. That would flip it upside down. So we could have an upside down bowl. So let's just tweak it ever so slightly. Z equals minus x squared over a squared plus y squared over b squared. Now, this one's fun to try to draw. I'm not very good at it, but that's all right. Let's do perpendicular to y first. In particular, let's set y equals 0. What shape do we see if y equals 0? It's a parabola that goes down. So it's a parabola. That's cool. So we would see a parabola going down in xz. So that's our shape. Again, that's if I'm slicing in the xz. In fact, anytime I fix y, I'm going to see a parabola going down. What's going to happen, though, is that as I vary y, I'm going to sort of do a shifting up. So I get these parabolas opening up. Parabolas opening down, but we're sort of dragging their vertex up. Now, suppose I do perpendicular to x. Let's say x equals 0. What do we see? See another parabola. But now, which way does it open? It opens up. It opens up. Okay. And again, if I vary x, what's going to happen? Well, I'm still going to get this z equal y squared, but then I'm going to subtract. So what it's going to do is it's going to like pull it down. Okay. So, all right. Well, what if we're perpendicular to z? Now, if I just set z equals 0, I get 0 equals minus x squared plus y squared, which turns out it's the lines x equal y. Let's suppose I vary z. Let's say 1 equals x squared. Sorry, 1 equals negative x squared plus y squared. What type of curve is that? 1 equals negative x squared plus y squared. It's a hyperbola. So these form hyperbolas. And the picture gets a little bit hard to see. So let me actually draw what's happening here. This is sort of the easy way to draw the picture. So that's our basic shape. Now, what do we call this? Well, it's still based off of parabolas. Those are our cross sections we see. So we're still going to call this, again, a paraboloid. But now we run into the problem. See, we have two things called paraboloids, and they are very different types of shapes. So the first type we talked about, we'll actually call it an elliptic paraboloid because the cross sections we run into are ellipses. The second type we talk about is a hyperbolic paraboloid because our cross sections would be hyperbolas. And what we mean by that is if you were to take a cross section, say up here, this green curve where we fix a z value, you would see that we're forming a hyperbola. Now, do we have a nicer name? This one we call the bowl. Does this have a nice name? Yeah, we call this one the saddle. And the idea is, if you were to actually imagine if you've ever been on a horse, there's this, you have the saddle. So, so you have to imagine that I could draw a horse, but I feel like my horse is more cow-like right now, but okay, so, all right. I didn't grow up in Iowa, so I'm not used to the farm life. I apologize. But imagine this was a horse. There's this saddle shape, and the saddle, you see in one direction, you have it sort of going in a nice shape, parabola, up, down, and then the other direction, you have going the other shape. All right. So Bulls and saddles. This is going to be a really important discussion later on in our semester. So, almost there. A few more things. Suppose we look at this one. And again, for convenience, suppose you think of a and b equal 1. X squared plus y squared equal 1. If you heard x squared plus y squared equal 1, what do you think in your head? You think circle, right? Because you're thinking two-dimensionally. But what if it's a three-dimensional setting and you hear x squared plus y squared equal 1? Well, what's the right thing? X squared plus y squared equals 1 is a circle in the xy plane. But what if I move z up? Say I change now, instead of z equals 0, z equals 4. What would I see? I'd see the same circle. If I move z down to a negative value, I'd see the same circle. So what happens is, because there's no z, I'm going to see the same shape going up and down. So when you have a variable missing, that doesn't mean that, it's a two-dimensional thing. It just means, make photocopies all the way up and down. So you get the same cross sections. And we have a name for that, and we call these cylinders. So when we say the word cylinder, what we mean is that there's essentially a missing variable. And what that translates into is that we get to just sort of sketch the curve in some plane, and then we copy it up and down. So normally when we say the word cylinder, this is, of course, what we have in mind. And if you see a problem that says, there's a cylinder, you should think, okay, this is a cylinder. But there's also a different variation. So here's an example. There's this surface, z equals sine of y. Now, what's not here? There's no x. So how do you sketch this surface? The answer is you start by saying, all right, let's look at just in the zy plane. So z equals sine of y, that's a curve we can sketch. And so we sketch our z equals sine of y. There's our z equals sine of y. Now the moral here is what you do is you just copy it. So I can come down and I move x forward, say, and I now sketch the same curve. So it's the same curve, I've just shifted x, and I can move it backwards, and I can sketch the same curve. And what do you do? Well, it's the same all the way across. So what it looks like is it's like this rolling sheet of paper that's moving up and down. And that's what the surface z equals sine y looks like. Okay, so the most important thing today that you need to remember, and we're going to keep referring back to and back to again, is not that I'm a bad artist, but that we have these two things, bowls and saddles. And these are going to be important as we go on later in the course. And that's it for today.